Our next presentation is entitled On Mounting a Robot. Elijah Williams is the Digital Technology Specialist at the New York Institute of Technology School of Architecture and Design Fabrication Lab. He teaches the fourth-year Comprehensive Design Studio team with a focus on advanced modeling and fabrication techniques. His design studio and work at the recently founded Studio Albatross in Long Island City focuses on hands-on model making, public data systems, and challenging formal design logics and their relationships to urban development. Elijah.
All right, hi everyone, can you hear me okay? Okay, so as you heard, I am not a professional mount maker. I am here representing, I understand very clearly why I was segmented here. I'm going to be talking about robots, talking about moving systems. These systems versus these two amazing presentations we just had are dynamic, meaning they are motor controlled, servo controlled. For those of you who are nerds, which a lot of you seem to be, you can essentially just think of it as Arduino for everything, right? Little inputs and outputs that drive powered systems. So I actually have like a kind of an overview of why that's relevant in the beginning of the presentation. But my hope, and I can get started in here, presentation is called On Mounting a Robot. As mentioned, I live and work in New York. I'm from Berkeley, California, a lot of Californians in here. And part of the difficult role that I hold in my weird kind of BS title, Digital Technology Specialist, is that I am in charge of all hard things that no one wants to allocate money for and work on projects. And so the most difficult one that I've had to deal with had to do with the budgeting and sourcing of mounting this giant robot that we're about to talk about. The flow, what's generally going on in schools, in museums, in labs with robotics. The problem is, quote, moving, right? What do we do with moving systems? How do we mount them strongly with the future movement of them as their main goal? These are not conserved objects, but as a way of talking about it, I'm going to talk about a kind of funny little one that I made. And then finally, what's the role of safety and strength in dynamic movement systems? I applied to this with some outside context, which is a lot of time that I spent traveling and working in Japan, and the role that 70s and 80s robotics play in museum culture there, right? So they obviously like kind of invented robots, and so they have these amazing systems for presenting why Japanese robotics are important in a museum context. And so I don't do that for work, but I thought that was really cool. That's actually what got me interested in the IMF and in mount making overall, was this idea that these moving systems need to be mounted statically, or in the case of this, dynamically. Okay, so this is my lab. This is where I work. We're on 61st Street. Hint, there's the robot on the final mounting in the background. We're on 61st Street, right next to the Lincoln Center, right by the Museum of Art and Design and the Folk Museum, if you've ever been there. We are on the 10th floor. My desk is just off to the right. That's my coworker, Fadil. We are the inbound for all research and student-led innovation projects at the entire school. The school has 2 campuses. You'll see some of both. We are the only staff that do all of that for both campuses, total about 20,000 students, focused on the School of Architecture and Design. So when students are trying to learn about robotics and dynamic systems, and we, of course, as you guys do, I'm sure, have limited budgets, what can we do? Well, we can start to build little crappy prototypes of robotic systems. These are $6 Arduino sensors, or Arduino servos driven by a $18 Arduino, held together with tape for fitment and crappy gluing. And this system was really important for the early prototypes of what we were hoping to do with the robotics lab. On the right, I'm holding what's a hand detection sensor. This is a $35 component from about 10 years ago that can identify individual finger points and map them into data sets. And so this mount, very simple rudimentary mount, had to be dynamic so that I could adjust and calibrate the distance between the robot, which is this thing here, and the hand sensor, which is here, right? So this is all coded. We use heard some CAD stuff mentioned earlier. In architecture, we always use Rhinoceros 3D, which I can't advocate for enough. Those people are amazing. It's a 20-person team out of Seattle. We also use Grasshopper for our dynamic system. So this is all live, meaning there's no hard-coded elements. All the data is being fed in here directly into the brain and then used to, it's going to move in a second. I'm going to show you it moving. Everyone's like, boring. So yeah, these two things are going to be moving live, which means calibration and setup. These are huge points for working with moving systems. Calibration of bases, calibration of tools, and calibrations of motors, meaning where is the ground, where is zero, and how do we, as the sort of technicians in the room, tell the robot what its environment is. I think there's like a conception that these robots are super smart and know a lot about they know nothing. They literally are these $6, even the giant one I'm going to show you, they're these little tiny dumb servos. They need every single thing to be explained to them, often using really 80s style interfaces. And so this is a really clear example for you guys to talk about how simple this kind of calibration needs to be, how you need to explain where zero is, where that origin point is, like if you're measuring with a ruler, where no-go zones are and all of that stuff. So this is a simple example of how this system works. So this hand tracker, this is an earlier version, this hand tracker follows the point, it searches within its data tree and moves this little tiny robot. A bit of a technicality, but this robot is not thinking or doing anything. It has a matrix of endpoints. It's measuring where the finger point is, and then it's taking its best guess at where the endpoint is. So seems a little, I don't know, a little, small to present this at the IMF. That's just glued on. But it works to get it started. It works to get students and educators excited about investing in these kinds of projects. And of course, a nice messy tool station here. Okay, so all of a sudden they get much bigger. So this is the KR10 R1100. That's some fun naming conventions stuff. This is the payload. This is in the naming convention of robots. They include the millimeter reach of the robot in the name and the payload ability. This is a really cool chart. I just assume you guys like charts, I guess. This is a chart that describes the length of the XY axis and the length of the Z axis of the robot. So these robots can reach around like a human arm, and how the payload ability, the ability for it to hold something on its end, how it falls off the farther away it gets from its origin point. Right? So the robots are really good at holding stuff up here. If you've ever seen the robots moving entire cars on production lines, they can literally lift entire cars. But if they start to come out, you can see extended not even 3/4 of the way, we start to have only 6 kilograms of payload, meaning ability to hold it up, versus if we're here, we can hold up to 10, right? So it's these are charts that come with robots. They'll come with any sort of custom powered system. But I think this kind of stuff's super important for explaining to bosses, curators, all these kinds of people what the actual ability of something is to do something. Everyone was so excited about this 10 kilogram number until you start to realize that it can kind of only put something within 1 foot of itself, right, if it's that heavy. I love the Mounting Motorcycle Legends. That was amazing. One of the cool things that it had me thinking about was axes. So this is what's called a 6-axis robot. So we have axis 1 here, which spins, axis 2 here, which rotates in this direction, axis 3, which repeats, 4, which spins, 5, 6, which is the spinning of this end joint. So these robots are fairly universal. A 6 DOF, 6 degree of freedom robot, is the standard for all robotic arms. For those of you that work with CNC machines, programming them is fairly similar to a CNC machine, except there's a couple more axes. So a couple of really important considerations that were not true for that tiny one that I showed you and are true now. This thing weighs 55 kilograms, about 110 pounds, and it's capable. This is so blisteringly fast, it's difficult to explain. 2 meters per second, right, for a giant hunk of metal. it is threatening to throw itself off of whatever you mount it on so hard. And so this is the system here in this photograph that we were given, essentially. This was already, this robot's on one of the campuses. We're talking about the other campus. This system is completely inadequate. This system is this rail aluminum rod with sort of a traditional, this is a shelving unit, basically, with pieces of wood attached in, and then a super thin piece of maybe 1/4 inch aluminum with the robot bolted in. The robots have 1, 2, 3, 4 bolt points and about 1.5 inches of steel base that the bolts is just 4 simple mounting points. We were the first team to really push these robots to the limit, and this robot is directly on top of the dean of the school's office, and we, the first day, got a complaint that her room was shaking, right? Because when the robot gets up to these speeds, the entire table was not only leaning, but also shifting and jerking back and forth, right? Simply because of the weight of the table, right? Why? Everyone's like, Elijah, this is my coworkers to me, Elijah, why are you so worried about this little bit of shaking? Well, on this campus, we're in some farmhouse out in deep Long Island, who cares? This is the view that the robot sees, right? Off the 10th floor down onto Broadway. So it throwing itself out the window was not an option. And this was sort of our truth chart here. So this is a welding table from Build Now. It weighs about 1,400 pounds. It has both a 1/2 inch top sheet and the one that we have does not, but many of them have these mounted side plates for what I was talking to someone over here, but about these mounted side plates for angle welding. You should be somewhat familiar with this kind of stuff. But each of these robots has a degree of freedom. This is the total range in which the robot uncontrolled can move. This also does a great job explaining the torque and fulcrum points of the robot. We had no option. We just had to overcompensate and get within our safety factor. As I'm sure you guys do, we would have loved to hire some structural engineers and talk about all of this stuff and get really in the weeds. That was not an option. It needed to be there for the first day of school. How do we figure that out? So what we ended up doing was procuring this $7,000 welding table that weighs 1,400 pounds and building this mounting plate system here. So this in green is that robot that you just saw. This is the mounting plate system, and this is the welding table. So in Rhino, we started to mock it up. We needed a system that was adaptable to the 2-inch by 2-inch grid of the welding table, which is fairly standard, and the somewhat random grid that the KUKA branded robots come with, right? So we were able to put out an order for basically 5 plates of 1/2 inch steel with a grid pattern on it, and in about 25 minutes, get the robot up on the table. This system, in reality, has multi-directions, multi-orientations, such that the robot can be moved around the table, can be rotated, can be shifted, and it looks like overkill, but I'll be honest, we're still shaking the table a little bit with that 2 meters per second, but we're able to decrease by just upping the weight of that base table. That tip factor is way down, right? Because we're not able to lift the weight of the table with the robot itself. I think the idea that there's a soft limit on these robots that some smart programmer put in to keep us safe is wrong. It's up to us. We needed a table that would off the robot instead of a robot that would off the table, right? So that's sort of how we went with this system. And so the sort of fun detail that we left is these hanging bolt holes, the slots underneath, so that the robot could be bolted directly to the top plate. The robot could stay mounted to the top plate. Top plate could be removed from the bottom plate and moved around, so the positioning of the robot on the table can be done without disassembling the entire system. For a variety of reasons, moving these robots is super duper important for the actual functioning of the movement of them. And so you guys can tell your boss you want one. Oh, here's the final positioning of it. It's still kind of close to the window, But the table is adjustable in leg height, the computer system all fits underneath, and that movement system, this is the sort of control plane for the robot. And finally, of course, here's the spec sheet for our table. Thank you, guys.
Thank you, Elijah. So I have one quick question. Seeing you're a little bit outside of our normal mount-making sphere, how did you find the IMF?
Do you want the real answer or the?
The real.
I think everyone threw the meme page, right? I think that's the. No. I obviously go to museums in the city all the time, and I attended years and years ago, a very small exhibit all about mounts on the Upper West Side on West 86th or something. I'm not even sure who it was, but I went with a bunch of curators who I was friends with from Berlin, and we were all sort of losing our minds. And I was like, there's got to be a weird community of people thinking about this. I was right, so yeah.
So I'm going to jump in with another one of my questions while we wait. You mentioned that in your little mock-up, which was awesome, by the way, made out of plywood and tape and glue. I love that. The little servo motors you said were from the 80s. Why from the 80s?
No, so robotics have not really come as far as people thought they had. Basically, not a ton has changed since the 80s. And so those robots that can do what I just showed, like the servo control systems are even older than that. They're from the 40s and 50s. And programming them is really dumb. Like you can program them on a dial. You can program them exclusively using electromagnetic pulses. And so they make people feel like they're magic. But if you've ever even thought about it, I can't recommend enough getting a $25 Arduino starter kit and building a crappy robot. It takes like 20 minutes. And it's really fun to do something. That one with the hand detection is a little bit more complicated, but making a little worm that jiggles around on the ground when you press a button, this is really within everyone's skill set. It's not some magical thing, which sounds ambitious, I guess. But I say that because these modern systems that look super complicated and expensive and get the sort of ooh-ah, those systems are computationally very similar to systems that have existed for coming on 100 years. So there's not some mythical other thing that technicians work on. That simple one is basically explaining the whole thing, yeah.
Yep. Hello. I have possibly a somewhat boring two-part question. One, are more contemporary robots made with larger base plates so that the movement of the robots aren't so likely to tear them off the tables? And how did you source, or what kind of bolts did you use to know that you had the tensile strength that you needed to hold? Those 4 mounting points just seem so close to the base. They really seem like they should be a foot or 2 feet away from the base of the robot on a very large cast iron plate to be much more safe just in the inherent build. So how did you source the hardware to know that those were not going to tear the arm off your table?
Yeah. To the first part of the question is, I think, a troubling answer, which is you can just order one of these robots. They don't tell you, there's no safety guide, there's nothing. They just show up. We just ordered another one. They're like $40,000. They're shipping it to us right now, and they don't care how we mount it at all, right? I don't know what they think we're going to do with it, but so this system, I think there's a piece to the second part that's relevant to the first part, which is these robots are not operated unsupervised or by students or random staff. They're operated by us. And so it means that a very select few people get to shake the robot and make the dean mad. Not everyone. And so there are really safe operating parameters that a lot of the stuff can happen within. And that's something that makes me a little bit nervous, but I feel confident in. And then for the shear strength, like I said, I would have loved to hire or be a material science engineer to figure that out. But we have a lot of great, I should thank, obviously, my whole team, which is my boss, Brian Polgar, who's the director of all the labs. We also have 2 amazing shop supervisors who actually run the day-to-day wood shops and metal shops for the students. And so we were actually able to take our problem of our strength of the bolts to them and talk through what they'd seen used in industry for building facade mounts, right? So when buildings are built, pieces of buildings get mounted on, and they have this really intense, not only gravity, but also wind shear force. And we were able to basically spec industrial bolts for that. But I'm not worried about shear force from robot movement in that plane. I'm worried first about tipping. I think if I rip it off in that direction, it falls out the window. I shouldn't have said that on camera. Yeah.
I think we have time for just one more question because we're starting to fall behind time a little bit. You had one question?
Part of it was answered. Thank you for talking about the control mechanisms, because I thought about in my career all the times visitors and members of the public have been creative in interacting with things. But I guess a simple question, does it throw off much heat as it's thrashing?
Oh, interesting. So actually I'm glad I put my little one in there. So these systems are super duper energy efficient. They're called servos. They use electromagnetic pulses. They don't really ever heat up, but they are not strong with resistance force. And so these systems that are inside this this is just an aluminum body that's holding, instead of a servo, a magnetically locked motor, and motors get super duper hot. And so these systems have temperature control modules within them that will auto failure if they get overheated from running. These are industrial robots for manufacturing, and so they can go. I think that in the most extreme of circumstances, I'm imagining mounting one of these that's running 10 hours a day in an exhibit. I do think heat would be a concern. I do think you would need to get from the robot company a spec sheet about how much, what prolonged runtime would mean and what good maintenance would be. These things are essentially CNC machines, right? So if you run them, they need to be maintained as well. Yeah.
Thank you.